Many engineering problems rely on the assumption of Gaussian distributed data. In a real scenario, this assumption may not hold, and the distribution of the data could be heavy-tailed due to outliers. Consider a wireless sensor network sensing the environment. In order to estimate the sample average of the readings across the network, the nodes should be able to dismiss wrong readings provided by faulty nodes. Otherwise, their estimator could be biased. The flow of the proposed algorithm is as follows. First, all the nodes sense some magnitude of the environment, for instance, the temperature. Second, they broadcast their sensor readings to their neighbors. Since this is a distributed algorithm, every node can only communicate within its neighborhood. Once every node has received data from all their neighbors, they can initialize their estimates, including the mean and variance of the data and the prior probability of a node being faulty. With these values, each node computes locally the a posteriori probability of a faulty node. This is named the expectation step. Next, the nodes broadcast their outputs to their neighbors. Once every node has received the updated information from their neighbors, they run a second computation stage to find some variables that are needed to re-estimate the model parameters. This is known as the maximization step. Finally, the nodes update the maximum likelihood estimator that will be used as model parameters in the next iteration. This expectation, diffusion, and maximization steps are repeated at every iteration of the algorithm until convergence. Our wireless sensor network testbed is composed of commercially available Econ modes that include a Freescale ARM7 microcontroller with 802.15.4 radio. The modes run Contiki operating system that provides multi-threading capabilities and low-power internet communication even for memory-constrained devices. It also offers the QGIS simulator that simulates the whole functionality of a network before burning the program into the hardware. Over the Contiki communication stack, we have implemented an abstraction layer that provides distributed computation capabilities, hiding within neighborhood communication from local computations. Let's see the testbed in action. We have deployed a network of 10 modes plus a sniffer connected to a laptop that we use for contract monitoring. First, we plug the modes into their USB batteries. The graphic user interface shows that the sniffer has detected the presence of the 10 modes. For each node, there are 3 values: its sensor reading, the estimated sample average across the network, and the robust estimator that is able to dismiss faulty nodes. The curves show in real time the evolution of the estimates given by the standard average consensus algorithm and the proposed robust estimator. Since no node is faulty, the robust estimator approaches the same value as the consensus algorithm. In order to see the robustness of the proposed algorithm, we force node 5 to be an outlier. Now, the nodes follow 2 different curves, showing the bias that node 5 introduces in the sample average. As a second experiment, we force 2 outliers. Again, there is a clear gap between the consensus and robust estimates. The more outliers, the less representative samples available for the robust algorithm to estimate the right distribution. Zooming the curves, we see how the robust algorithm approaches the ideal estimator more slowly. In our last experiment, we force nodes 4, 5, and 6 to be outliers. With 3 outliers, there are only 7 valid samples available for the robust algorithm. Hence, we can see how it approaches the right estimate even more slowly. The experimental results obtained with the real hardware are similar to the numerical results obtained by simulation. We hope you have enjoyed this demo. Bye for now.